Okay, so today is a big question session, so it's really your day today. Today's Thursday, November 12th. Thursday, November 12th. Again, saluting the veterans all the time, but especially yesterday, Veterans Day. Uh, okay, so remember that the homework for chapters 5 and 6 will be due tomorrow, which is Friday, November 13th, Friday the 13th. So you can watch your horror movie marathons tomorrow, right? And chapters 5 and 6 will be due then. Chapters 5 and 6. All right. 6-5 was cool, but it was optional. There was no homework. Okay, so that's going to be due Friday, November 13th, end of the day tomorrow. Now, on Tuesday, we started chapter 7, and I do encourage you to at least do 7.4, number 1 by next Tuesday, because we're going to finish with partial fractions next Tuesday. So it's good to get a review of that stuff. So even before you do the system stuff from earlier in chapter 7, although some of you need that review also, but especially do 7.4 number 1 by next Tuesday, so we can continue with that and try to finish the rest of 7 also. Okay, 7.5 and 7.6 were optional. Okay, they are optional. And we'll continue with chapter 8 with matrices next week. All right, and now again, regarding the grades, you should have the grades for chapters 0 and 1 returned back by now, okay? So for the rest of the semester, including the Thanksgiving break, I'll be grading. So it'll be this trickling through, all right? Don't forget there's also Alex for extra credit, okay? All right, so, and wow, yeah, look at all these. Now, you might want to take a screenshot, or remember that this will be in the video that I'm recording now, but this is a reminder of the various questions that I've covered in the videos. And as you've seen in my grade reports for chapter 0 and 1, it's very convenient for me to point people to videos for solutions. Also, it kind of makes sense that I would tend to gear myself towards questions that we address in class and after class, right? So yeah, it makes sense that I would have a tendency to grade those kinds of questions, right? Uh, Not necessarily all of them, but possibly, okay, but again, on the office hour from, I think, Monday of last week, okay, I covered these 6. Last Thursday, I covered 5.1 2b. Oh, no, maybe that was, oh, maybe that's right. That's right. Yeah. Okay, and then this past Tuesday, maybe last Tuesday, I'm getting confused too. Last Tuesday. Last week Tuesday. Okay, I did 531N, and then last week Thursday, obviously not tonight. Last week Thursday, right? I did these. Again, not necessarily in this order, but here I actually ordered them. Yeah, these are in order for this week Tuesday, the Tuesday that just passed, November 10th. I went over these after class, so you can check the class video again in order. That's why 6.3 is after 6.4 in order from the video. All right. So again, you're putting questions in chat, right? Or if you want to, yell out at me, that might be okay, maybe. But I think chat would be ideal. Are there any general questions before I proceed with the chat questions? Any general questions before I proceed with the chat questions? Okay, we are recording. Okay, I'm going to post this recording by midnight or so, or early Friday. Okay, so we're ready to start the chat questions. Okay, so keep adding to chat. And let's go in order. All right, I'll save this. And remember, the homework is due end of the day tomorrow. End of the day tomorrow, Friday the 13th. Okay. I'm going to go over here now. All right, so let's open. And I indicated here which ones I've already done in the videos. Let's see, let's do 531L is our first request. All right, 531L. Right, it was wise of you to capitalize the L. Yes. I've come to do that too, capitalizing the L so it doesn't look like a 1, right? Okay, so I'll do that in blue here. All right, let's do it. I don't think I've done this before, right? Okay, so, whoops. Although that's interesting. All right. All right, so this is 531L. All right. Now, you don't have to rewrite it, but I will rewrite it. As a student, it might help you for your reference to rewrite it. Okay. All right. Okay. Tangent squared of theta plus tangent of theta equals 0. Okay, now right off the bat, some of you might want to substitute. You don't have to, but I think substitution might be a useful trick here. Let u equal tangent of theta. You don't have to do this, but I think the factoring may be more straightforward if you do. So if you apply that substitution, all right, you get u squared plus u equals 0. That looks a lot more appetizing than factor. All right. Now, I know you might be tempted to divide by u, but be very careful about that because you don't want to lose solutions where u is 0. So it's better to factor. Okay, better to factor. U times the quantity u plus 1 equals 0. That's the key algebra phase of this problem. And then by the zero factor property, u equals 0 or u plus 1 equals 0. And therefore, subtracting 1 from both sides, u equals -1. And that completes the bulk of the algebra phase of this problem. Okay, if you have any questions, I'll try to check the chat here. All right. But now we got to go back to trig. It was a trig problem, wasn't it? So let's go back to trig. I'll go ahead and do this in green. All right. Well, how about a different color? How about purple? All right. So u was tangent of theta. Tangent of theta equals 0. Again, you don't want to divide by u on both sides because you might lose these solutions. Right. Although a common trick in Math 255 differential equations is to do something to like divide by u, but then you have to consider u equals 0 as a special case. All right. Anyway, got to consider tangent of theta equals 0 or tangent of theta equals -1. Okay. Now, sometimes there's a great overall symmetry, like the peace symbol or anti-peace symbol, but here it turns out that won't be the case. I'll just do this bit by bit. In fact, I'll just scroll up. Let's focus on the unit circle here. All right, so unit circle here. When I see tangent, I think what concept? I think slope. If you consider lines that go through the origin, what 2 points correspond to 0 slope? What 2 points correspond to 0 slope? I think you're going to get east point and west point. All right, those correspond to 0 slope, a horizontal line. Well, what are the angles that we associate with these points? Well, some famous angles are 0, pi, 2 pi, and so forth. You don't even have to write these down. In general, what do we get? Theta equals basically integer multiples of pi. Pi n. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. Also going clockwise. -1 pi, -2 pi, -3 pi. So theta could be any integer multiple of pi. I'll put this at the end, where n is an integer, right? Or, well, a -1 is certainly a slope. It's a tangent value. All real numbers are. What's the deal with tangent of theta equals -1? In what two quadrants is tangent negative? Negative. Negative slope, where they can whoosh, whoosh, whoosh. All right.
2 and 4.
Quadrant 2 and quadrant 4. Very good. And of course, they're brothers. Kitty corner from each other. But now you're going, uh-oh, what are some famous angles we associate with this, with these guys? Well, wait a minute. It might be better to consider the reference angle. I'll do this in red. Is that red? Yeah. Okay. So tangent of what is positive of 1? In other words, what's the inverse tangent of positive 1? What's this guy I'm dashing here? That's going to be pi over 4, right? You should know that tangent of pi over 4 radians, or 45 degrees, is 1. You should know that. Now, that's not a solution for theta, but it's the reference angle for all our solutions. So again, even though pi over 4 itself is not a solution for theta, it is a reference angle. It's the reference angle for all these solutions. Okay, so let's remind me of these brothers here. Who's our favorite brother for pi over 4 in quadrant 2? Well, 3 pi over 4. 3 is 1 less than 4. It's pi minus pi over 4. And then a nice brother over here. Well, it depends. What are we looking for here? We're looking for both all real solutions and the particular solutions between 0 and 2 pi. So I'm a bit torn here. For all real solutions, I'm inclined to put negative pi over 4. Because it's the easiest, right? If you know this is pi over 4, then this corresponds to negative pi over 4. But later on, when we get the solution between 0 and 2 pi, we might rather consider this to have the representative 7 pi over 4. We'd rather have 7 pi over 4 as the representative if you're more concerned about this issue over here, solutions in this interval. All right, but for right now, for the general solution, for all real solutions, all right, I'm going to say it's the set of all theta values in the reals such that theta is of the form pi n, or theta is of the form plus, oh, wait a minute, wait. I don't want positive pi over 4. So I could do this. Negative pi over 4. You could start at negative pi over 4. And then how do you get the other solutions? By doing half revolutions. How many radians are in a half revolution? How many radians are in a half revolution? Counterclockwise, let's say. Pi radians. And we want an integer number of half revolutions. Either counterclockwise, in which case n is positive, or you stay put, in which case n is 0, or you go clockwise, in which case n is negative. You don't need plus minus because n could be negative, where n is integer. And I'll put this in black here, the box. I would accept this as the final answer. Now, let me check to make sure that I'm matching my own answers. Okay. Is this a form I give? This is 531L. Yes, it's a form I give. Theta equals theta equals pi n, or theta equals negative pi over 4 plus pi n. Although, if you prefer the non-negative angles, and we tend to do that if we're concerned more about this interval, right? Instead of negative pi over 4, you could put positive 3 pi over 4. And that's also fine. Remember, over here, you can put any representative for either point. So if you like the negative pi over 4, you can put that there. If you want to put the 3 pi over 4, you can put that there. If you'd rather have 7 pi over 4, you can put that there. You can put any representative of either point and then put plus pi n. Now, if you don't like using too much symmetry, you could do a rep here plus 2 pi n, or theta could be a rep here plus 2 pi n. That's kind of overkill, but I'm not going to mark you wrong if you give me a correct solution, even if it's not the most efficient, assuming that's reasonable. All right. Any questions here? Any questions here? Again, you could let 3 pi over 4 be a rep there. And then what are the solutions between 0 and 2 pi? It's these 4 guys over here. So we're playing around the world. Okay, I'll circle in black. I'll circle the guys we want. Okay, 0 itself is a solution. We go around the world. Now, pi over 4 is not a solution. It's a reference angle for some solutions, but it's not a solution itself. 3 pi over 4 is a solution. Pi over here, west point, that's a solution. And 7 pi over 4, right? If we want solutions between 0 and 2 pi, we only want the 7 pi over 4 representative for this point. Okay, and those are the 4 solutions I get in my answer sheet. 0, 3 pi over 4, pi, and 7 pi over 4. Remember, you don't have to order these. You don't have to sort them, but you have to have all 4 of these in some order, separated by commas. All right. Any questions about that? Any questions about that? Okay, I have a question in chat. How much of that work do you need shown on the homework? All right. Now, remember, you don't have to do the substitution here, but it's more writing, actually. We can skip this step, but it's more writing, actually, if you don't do it. So you don't have to do the substitution, but you should show the factoring. You should show some factoring. Again, you don't have to label over here. If you indicate the east point and the west point, then I believe you when you say that the representatives are of the form pi n, where n is integer. Here, I think it's nice to at least draw some sort of picture. But basically, I'm being pretty efficient here. Okay, don't try to skip too many steps. I think I'm fairly efficient here, except for the fact that I'm really calling out some of these angles on the picture. But even something like this, again, you only need 1 rep for 1 point. So I'm doing over labeling even for this. All right, so aside from maybe the labels and the fact that you don't have to do the substitution if you don't want, I do pretty much want to see all this work, pretty much. Okay, remember, when in doubt, show more work. You want to you want to be clear to a competent colleague who might need to see things step by step. All right. Okay. So I think that's 1L. All right, let's go to 6-3, number 7. Okay, and also I want to save these. I definitely want to save these. All right. 6-3-7. Ah, yes. Kind of a conceptual question here. I'll do this in green. All right. So going over here, I might be doing more typing on this one. All right. So so this is 6-3-7, right? Okay. Okay, now it might actually be more helpful to write these in component form. So we're dealing with the vectors. So 3i plus 4j in component form is just 3, 4. And then this vector here, 15i plus 20j in component form is angle brackets 15, 20. All right. So let's say that this is v, and let's say this is w. When do we have vectors that point in the same direction? If and only if this is true. Okay, so these vectors have the same direction. I'm assuming these are vectors in the plane. These vectors have the same direction if and only if, first of all, we need one to be a scalar multiple of the other, right? Okay. So for example, it looks like W is bigger. I'll do it. W has larger numbers here. W equals C times V. I should put my little half arrowhead guys here. W equals C times V for some value of C. Okay, now first of all, again, when is W pointing in the same direction as V? If W has the same direction as V, that's when W is a scalar multiple of V. I mean, and notice these are non-zero vectors. W is a scalar multiple of V, where C, the scalar multiplier, is positive. Because if C is zero, you get the zero vector. The zero vector has all directions. Kind of weird. If C is negative, you're pointing the opposite direction. Okay, so the question is W a scalar multiple of V where the multiplier is positive? Well, 15 is what times 3? 15 is 5 times 3, right? 15 is 5 times 3. Is 20 equal to 5 times 4? Is the common ratio here 5? Is there a common ratio? Yes, there is. 15 to 3 is 5. 20 to 4 is 5, all right? So in other words, I'm saying here that the vector W is in fact 5 times the vector V. All right, so if you want a succinct explanation, do these vectors have the same direction? The answer is yes. Why? Because W is 5 times V. W is 5 times V, and they're non-zero vectors. So in a way, that's a more succinct way of putting it. These vectors point in the same direction because one is a scalar multiple of the other, where the scalar multiplier is positive. W here is 5 times V. All right. Questions about that? Questions about that? All right. So now please interject if you have any questions there. That was 637. All right. 621C and 558A. Okay, let's see here. All right. 621C. So I'm sure this is the triangle inequality here. I'll do this in blue. Purple. Okay, 621C. Do I have the check the answers here? Okay, so yeah, as I suspected, no, this isn't possible as because of the triangle inequality. Okay, so yeah, I was going to see if I had drawn a triangle, but I didn't draw a triangle. I guess I'll label this directly here. Okay, so I'll label directly here then. All right, so we know that the incline is length. Okay, so little a is 52.7 feet. B, the distance from the observer's shoes to the base of the hill, that's going to be 29.4 feet. Okay, C is 77.6 feet. Now, someone claims that the observer shoes are actually 9.4 feet. So someone's saying, hey, I think you made a typo. I think this is actually 9.4 feet. Is that possible? Here's the thing. Let's say that your place, your apartment, your house is at point A, and the supermarket is at point B, and you want to go to the supermarket along this straight street. Okay, the straight line distance, I guess the distance as the bird flies, as they say, is 77.6 feet. But here's the thing. If you take these two side streets, shouldn't this path be longer? If this is the straight line segment distance and it's 77.6 feet, wouldn't you expect any detour to be longer? Here's the problem. 9.4 feet plus 52.7 feet, that's way below that. So there's no triangle with these kinds of side lengths because you would violate the triangle inequality. The triangle inequality basically says that any detour cannot be shorter. And for a bona fide triangle, a detour has to be longer compared to the straight line segment length. Any questions about that? One moment. My throat's going to get dry, so I'm going to need to drink some water from time to time. So as I do that, keep putting questions in chat. I need a drink of water right now. One moment. I'm going to have to do this a couple times. All right. Okay. All hydrated there. Okay. Any questions? Okay. So that was 621C. All right. And then 558A. 55. Or 5455, right? 5455. 8A. Yes. So here, I remember I started this. I circled this. I started this in a previous after class session. Let me retrieve that. Oh, here it is. Here we go. So I started off with some students. All right, so take a look here. Take a look here. So remember, this was the kind of problem that I had you conjecture back in chapter 4. So back in chapter 4, I could have given you this kind of problem. Why does that identity make sense? All right, so here's the unit circle, right? Assume for now theta's acute, although it doesn't have to be acute. So let's say theta corresponds to this point. Where's theta plus pi? It's going to be kitty corner here in quadrant 3, theta plus pi. What does the sine value correspond to? It corresponds to the y coordinate of the corresponding points on the unit circle. Are these y coordinates equal, opposite, or neither? Even as theta varies over the reals, they're always going to be opposites. The sine for theta plus pi will always be the opposite of sine of theta. That's true for all real radian measures for theta. Okay, so that conjecture you should have gotten from chapter 4 ideas. Now we're going to prove this using the sum identity for sine. From the sum identity, sine of theta plus pi equals, it's the sum of the mixed up products. Sine of theta times cosine of pi plus cosine of theta, sine of pi. In fact, you can write this in different ways. So what's the deal with pi radians? What are the sine and cosine for pi radians? Okay, this point corresponding to where the angle is pi radians, its coordinates are what? -1, 0, where which is which? The cosine value is like x, the sine value is like y. So cosine of pi is -1. Make sure you put parentheses, some grouping symbols. So it's sine of theta all times -1 plus cosine of theta times sine of pi. What's sine of pi? The y-coordinate, vertical coordinate here is 0. This is 0. Therefore, all that's 0. So we're left with what? The opposite of sine of theta. The opposite of sine of theta. QED, all that jazz. We like what we see. Voila. So it's a matter of being brave enough to apply the sum identity, even though it's kind of weird looking, this expression you see here, and then remembering the data sheet for pi radians. The cosine value was -1, sine value was 0. All right. Okay. So all right. So next up, 6-4, number 9. Okay, so trying to hint at that. 6-4. By the way, if I skip anyone, please don't take it personally. It's just kind of tricky to follow the chat order sometimes. All right, right. Okay, so kind of a wordy problem here. No, wait, 6-4. That was 6-3, 6-4. Oh, okay, yeah. All right, what's going on here? Yeah, I'm going to pull up another whiteboard. Electronic whiteboard. Here we go. All right. Let's go back to blue. Okay, and this is 6-4-9. All right. Well, maybe the axes might help me to sort of frame things. Frame in a broad sense, kind of figure out where points are. Okay, so 4-7 over here. You don't need a ruler or anything, or graph paper. 1-2, like that. B, C, 6-3. Maybe like that. Again, you don't have to be super accurate, but it appears that angle ABC, this over here, is going to be an acute angle. I think it's going to be acute, although I wouldn't put it past myself to draw this thing poorly. All right, so we want to know the measure of this angle here. Yeah, I apologize. My throat's kind of dry today. I'm going on, but I'm going to need to drink of water from time to time. All right, now, in order to find this angle here, I want to find the angle between the vector BA and the vector BC. All right, we want to find the vector BA and the vector BC in component form. Okay, so I'll go ahead and type in the coordinates. A has coordinates 4, 7. B has coordinates 1, 2. And C has coordinates 6, 3. All right. Some books, when they do this problem, they have you find all the angles, but I think I can get the point across to just have you find one. All right. So how can we represent the vectors BA and BC in component form? All right. So what's the deal with the vector BA? Or you can call them the vector V or something if you want. But the vector BA, and I don't want to be hypocritical. I want to put the half arrow thing whenever I have a vector, right? Okay, and I can't really boldface. Okay, so the vector BA, so that's going to be, what's the component form for that, the representation? All right. BA, it's kind of like we're walking from this point to this point, like on a treasure map. So what about the horizontal, kind of like your X component? Remember, it goes new minus old, right? We're walking from point B to point A, and yes, order matters. order matters, right? The direction of that arrowhead does matter. Otherwise, here you'll get an acute angle, right? If you draw it this way. Okay, so it's new minus old. So it's going to be 4 minus 1. Our x component is 4 minus 1. It makes sense because you're walking from point B to point A. You're basically walking 3 meters east. All right, so BA is 4 minus 1. You don't have to write that if you write 3, but 4 minus 1, comma, 7 minus 2. New minus old. All right, so that ends up being 3, comma, 5, which makes sense because generally speaking, this vector BA is pointing in a northeasterly direction, right? So, and 3, comma, 5 it does basically point in a northeasterly direction. All right. Now, what about the vector BC? It's a very similar process. Again, I want my arrowhead. Okay, BC, once again, new minus old. New x is 6, old x is 1. Comma, new y is 3, old y is 2. 1, comma, 1. Do I have that hit in the notes? Sometimes I have hints in the notes here. Well, find the vector angle between B and BC. I think that's correct. And again, 1, comma, 1, 5, comma, 1. 6 minus 1 is 5. I see that's one advantage to drawing a sketch because I'm going, that ain't 1, comma, 1. Yeah, 5, comma, 1. So that's one advantage of doing like a quick sketch with broadly reasonable accuracy, not perfect accuracy. Okay, so the vector BC can be given by angle brackets 5, comma, 1. 6 minus 1 is 5. 3 minus 2 is 1. And then you want to find the angle between these two vectors in either order. And that's where this formula comes in handy. I'll look at my notes here. Angle between two vectors, that's 6. That's 6.4. There we go. Voila. If theta is the angle between two vectors, v and w, cosine of theta equals v dot w over the magnitude of v times the magnitude of w. Or more succinctly, it's the dot product over the product of the lengths. Cosine of theta equals the dot product over the product of the lengths. Right? For example, v could be 3, comma, 5. W could be 5, comma, 1. But it doesn't matter because we have commutativity for the dot product and we have commutativity for regular multiplication of scalars. So it doesn't matter what order you do these in. Cosine of theta equals the dot product over the product of the lengths. The order does not matter at this stage. Did I say phase or stage? All right. Okay. And then when you work that through, what do you get? To the nearest tenth of a degree, you should get about 47.7 degrees. I'll give you a moment. See if you can get that. I'll give you a moment to try to calculate that. Remember, you're going to need inverse cosine.
Wait, what was the formula again?
Yeah. So cosine of where do I have it? Yeah, over here. It's in section 6.4, part C, the angle between two vectors in section 6.4. The cosine of theta, that's the angle between the two vectors, is equal to the dot product over the product of the lengths. I'm assuming that these are both non-zero vectors, all right? The dot product over the product of the lengths. And then in the end, you're going to need to do the inverse cosine. The main reason why books don't put inverse cosine directly is that when they use inverse cosine, they normally like radian outputs. I'm personally okay with you using inverse cosine even for degree outputs. So if you want to put theta equals inverse cosine of that, I'm okay with that. You are eventually going to have to press in inverse cosine on your calculator. Any other questions? So you want to find the component form of these two vectors. Again, the orientation matters. You want the vector BA, not the vector AB, because if you switch the order and the arrow goes this way, you're going to get an obtuse angle. So you have to make sure that the orientation is going in the right direction. All right. Any questions? Any questions? All right, let's see here. Yeah. A student is commenting that, yeah, this was the tricky part, and I agree. Yeah. Finding component forms for these vectors. Right. Okay, now 531M, I think, is next. Again, please don't take offense if I skip someone. It's just following the order here. 531M. Yes, it looks bad, although he's not as bad as he looks. Maybe I have to eat my words, but okay, I know it looks bad. All right, so let's do purple. Let's do purple. Yeah, purple. All right. All right. So this is 531M. I'm definitely going to need a new whiteboard for this. Okay, by the way, this is 649. All right, let's see, 531M. Five 1M. Okay. Now, again, it's up to you whether you want to rewrite the original equation. I might suggest it for your benefit and your eternal notes, right? Okay, but right off the bat, I'd like to do a substitution. Do this in green here. All right, so let's do this substitution. You don't have to, but let's let u be cosecant of x. All right, and then what do we get? All right, so we get, after we perform the substitution, u to the fourth minus 3u cubed plus 2u squared equals 0. Many of you will be tempted to divide by u squared. Don't do that. Factoring is preferred to division because you don't want to lose cases where u squared is 0. All right, so let's factor out u squared. We have u squared minus 3u plus 2 equals 0. All right, this does factor old school. I'd have to be in a bad mood for you to force you to use the quadratic formula. All right. U and U, same sign, both negative, if it's going to work at all. Okay, either order, 1 here, 2 here, or vice versa. Negative 2u minus 1u is negative 3u. So I have a complete factorization of this polynomial in u over the integers. Over the reals, in fact, more generally. All right, question so far. Question so far. All right. By the zero factor property, when does this happen? Well, u squared could be 0, in which case u itself has to be 0. All right. Or u minus 1 could be 0, in which case u equals 1. or u minus 2 equals 0, u equals 2. All right. So we finished the primary bulk algebra phase of that problem. Any questions before we go on to the trig? We've essentially done the bulk algebra of the problem thus far. Any questions? All righty. The first one is surprisingly easy. I'm going to go to blue now. All right. U equals 0. What was u? Cosecant of x. Oh, by the way, before I forget to mention this, a lot of students try to flip these to sine, powers of sine of x. You're not allowed to do that. Listen to me, folks. As a general rule, you cannot take reciprocals term by term. You cannot take reciprocals term by term. So you have no right to just flip these to sine to the fourth, sine cubed, and sine squared. You have no right to do that. Okay, there's no rule that says that you can just take the reciprocals term by term on one side. In any case, on the right, what's the reciprocal of 0? That's messed up. Okay, so let's make that clear. Now, at this point, we can consider the reciprocal idea. So wait a minute. Cosecant of x equals 0. When does that happen? In order for that to happen, sine of x would have to be undefined. But wait, is sine of x undefined for any real value of x? No, that's a dead end. Also, in case you forgot, let me show you something here. You didn't think chapter 4 would be biting us. Well, I'm going to prove you wrong. All right. Check this out. Y equals cosecant of x. Hey, check this out. Remember this up, u, down, u graph for y equals cosecant of x? Notice something. This graph does not have any what? This graph does not have any what? Correct. Excellent. This graph has no x-intercepts. What does that mean? Cosecant of x has no real zeros. Hint, hint. Cosecant of x has no real zeros. That corresponds to the fact that there are no x-intercepts on this graph. Okay, this red graph never ever hits the x-axis for either y equals cosecant of x or secant of x. So that's one of the benefits of cosecant of x and secant of x. They're never equal to 0. So for example, if you're solving an equation, you have the right to multiply or divide both sides by secant of x, cosecant of x, any power thereof, and you'll be cool. Integer powers, and you'll be cool. All right. Which means, hey, cosecant of x has no real zeros. This, ladies and gentlemen, again, dead end. That's the long and the short of it for this first case. Dead end. There's got to be a horror movie named that, Dead End. All right, dead end. Okay. Or you just cross that out. You don't have to write dead end. Cross that out. That's fine. All right, so that's a dead end. But you have to show me. You have to write out cosecant of x equals 0 and then maybe cross it out or something, or cross this out. You have to indicate to me that this is a dead end. All right, so far, no real solutions. But it turns out that over here, when we go to cosecant of x equals 1, we are going to get some real solutions. All right. Now, since that's defined and not 0, I can take the reciprocal of both sides. What's the reciprocal of cosecant of x? It's sine of x. What's the reciprocal of 1? It is 1. That makes sense because cosecant of x is 1 for exactly those values of x for which sine of x equals 1. If you don't believe me, think about the idea of the guide graph. Remember, if we have an x value, right, like over here, pi over 2, maybe I should scale these by pi over 2. X-axis, step, pi over 2. Yeah, okay. So notice here, at pi over 2, the sine value is 1, and so is the cosecant value. That makes sense, because when sine is 1, so is cosecant. When sine is -1, so is cosecant, all right? So again, when is cosecant equal to 1? When sine is equal to 1. So when does that happen? All right. What point does a sine value of 1 correspond to? Okay, what point do we associate with a sine value equal to 1, I should say? That's going to be Santa, as opposed to Satan over here, Santa. Well, actually, in Dante's Inferno, Satan's at the center. But anyway, North Pole, Santa. Okay? And what's the most famous angle we associate with this North Pole? It's going to be pi over 2. I hope you remember sine of pi over 2, or 90 degrees, is 1. All right? So we're getting solutions. The set of all x in the reals such that x is of the form pi over 2. And I want all the coterminal buddies. How do we get all the coterminal buddies? Plus 2 pi n, where n is integer. I'm not done yet. Remember, case 1 was a dead end. Case 2, we did get some real solutions. In fact, infinitely many. We're not done yet. We're not done yet. Case 3 will actually give us some more solutions. Any questions thus far? Questions thus far? All right. Now you might be thinking, hey, wait a minute. Sine of x cannot be 2. But folks, remember, the substitution was not sine of x. It was cosecant of x. So let's be a little careful here. I know you see the 2 and you go, oh, it must be dead meat there. No. Oh, I want blue. We want cosecant of x equals 2. And 2 is in the range of cosecant of x. Does this red graph pick up the y-coordinate of 2? Yes, it does, infinitely many times. When does that happen? Well, admittedly, we don't like cosecant very much. We prefer sine, all right? We can take the reciprocal of both sides because that's not a 0, and it's defined. The reciprocal of cosecant of x is sine of x. The reciprocal of 2 is, leave you in suspense, is 1/2. All right, so let's take a look at the unit circle for this third branch over here. In what 2 quadrants is sine positive in value? Positive. It's like the y-coordinate on this circle. Quadrants 1 and 2. Good. All right. Now 1/2, remember, that's kind of the low guy. Remember, 0.5 was actually one of the lower numbers. It's kind of flat, actually. So what's the reference angle here? Which is it? Is it pi over 6 or pi over 3? Which gave us the flatter terminal side here? This was pi over 6, or 30 degrees. Again, that's something a physics prof can snap quiz you on. I know physics professors who do this. Quick, what's the sine of 30 degrees? And you say, altogether, 1/2. Sine of 30 degrees, or pi over 6 radians, is 1/2. That's the reference angle for all our solutions. But now remember, we're not able to use symmetry about the vertical axis so well unless you have west point and east point. So what's a famous brother we'd like to pick up in quadrant 2? Methinks 5 pi over 6. Okay. The trick is 5 is 1 less than 6. You can also verify that this is what you get when you have pi and you backtrack pi over 6 radians. All right. So going to red. Right. Or x could be of, oh, actually I have a couple of things here, huh? Or x could be of the form pi over 6 plus 2 pi n, all the coterminal twins, or x is of the form 5 pi over 6 plus 2 pi n to pick up the coterminals. Now I know many students might be asking, well, can't we do some sort of trick here with pi over 6 and 5 pi over 6? It's not so nice. Because to do that, I think you're going to pretty much have to do pi over 2 plus or minus pi over 3, yeah, and that's not very pretty. Okay, so you don't really have much of an alternative but to break things up like that. Okay, end brace, and I hope this is an acceptable solution set. It turns out there's no good overall symmetry. If this were down at South Pole, we can get, I guess, the war symbol. Okay, I think that's the solution for 1M, 531M. All right, so pi over 6 plus 2 pi n, or pi over 2 plus 2 pi n, or 5 pi over 6 plus 2 pi n, where n is integer. Okay, time for me to do a Snoopy dance. Okay, my camera's not on. I can do my Snoopy dance. All right. I'm actually shocked I got my own question right. Okay. All right. Again, no good overall symmetry here. If this were South Pole, we could get the war symbol. Question so far. Question so far. Oh, you're very welcome. Yes, that was very instructive. And again, folks, remember, because I see this a lot on exams, when we had exams, don't take reciprocals term by term. We don't have a rule for that. You can take reciprocals of both sides if you're dealing with defined things that are not zero. But for something like this, do not take reciprocals term by term. Okay, you do not flip these to powers of sine. And anyway, what's the reciprocal of 0 anyway? That's messed up. All right. Okay, now I'm going to leave these on. I'll give you some time to digest these, because I'm a plant right now. I need water. I need lots of water. Okay. Well, I'm going to go on for about 10, 12 more minutes. Then we'll take our 10-minute break, right? But of course, you can still put stuff in chat. Okay, any questions there? Very instructive. If you can do this, then you're very well set in terms of equations. All right. Let's see here. 1M. Okay, 521E, I believe, is next. All right. Yes. I believe I have this in both a video. Yeah, I have it in a video, and so what I can do here is I'm going to bring up my notes for this, and I'll refer you to the video. We did cover this last Thursday, 7 days ago. If you check the after hours video, maybe not in this order, but I did do 521E in that video, and I also reviewed it on Tuesday. After class, I did a review on Tuesday, but I can also do another review. All right, so 521E, let's do another review of this. All right, I know I have notes for this. By the way, I'm gonna move these up here. Okay, let's see, 521E, I have notes for that. Yeah, here we go. Here's part 2. Here's part 1. There we go. Okay. All right. So pros and cons to the tablet. I can write faster, but I think I'm a little bit messier though. All right. Anyway, so left-hand side was just this piece here without this over here. I should have put a times here, by the way. Oh, I just move him. Yeah. All right. Okay. So the left-hand side is over here, root 1 minus cosine of theta over his trig conjugate, 1 plus cosine of theta. Okay. So left-hand side, you should indicate what side you're starting on. So either rewrite the side you're starting on, or just write LHS for left-hand side or RHS for right-hand side. The left-hand side was just this piece without this guy over here. All right, so that equals, basically I'm taking this radicand and I'm multiplying by 1. Don't worry about domain. All right. Now, why am I multiplying by 1 minus cosine of theta over 1 minus cosine of theta? I can give you 3 reasons. Okay. Reason 1, you see that the left side's the bigger, uglier piece. You want to kind of smooth it out to make it look like the right side. Well, what can we do with this? Well, we can think trig conjugates. Okay. Because we have like a 1, we have minus plus, we have cosine of theta. We're thinking that trig conjugates might be helpful to go from left to right. That's one reason. A second reason, look at the target. We want 1 minus cosine of theta without the radical up on top. So that would suggest that I basically want to multiply the square root of this by itself, in the sense that, you know how if x is non-negative, the square of root x is x. In other words, if x is non-negative, maybe I should have written that note there. If x is non-negative, then the square root of x times itself is x, right? Like root 3 times root 3 is 3, and so forth. So that suggests that I want to multiply the top part of this fraction by his twin. And then that will ultimately have the impact of trying to remove the radical up on top. On the bottom, we're going to try to force a Pythagorean so we have something involving sine. All right, so that's the idea. The general strategy of a trig conjugate, the fact that if I multiply this guy by his twin, then I should be able to remove the radical eventually. And then the idea that I want to force a Pythagorean identity down here so that I eventually get a sine deal down here also. Okay, so 3 general reasons why I'm doing this. All right. Again, questions in chat. I'll keep an eye on the concept questions down here. All right. Now, when we multiply inside the radicand here, all right, well, just like x times x is x squared, this guy, 1 minus cosine of theta times his twin, you get the square of 1 minus cosine of theta. So if you believe that x times x is x squared, then you should believe that this times this is that, right? It's the square of this guy times his twin. All over, okay, either by foiling or if you have the sum times the difference of the same two guys, you want the square of the first minus the square of the second. 1 plus cosine of theta and 1 minus cosine of theta. When you multiply them, you get 1 minus cosine square theta. Basically the square of 1 minus the square of cosine of theta. Or we could FOIL it. That works too. But now wait. There are several observations I can make here. All right. First of all, the radical does break up. Basically, if these things are positive, let's say, the square root of a quotient equals the quotient of square roots. Basically, the square root sign breaks up across the top and the bottom. All right, so I'm breaking up the radical. Over here, the square root of blah, blah, blah squared. What's a way of simplifying the square root of x squared for any real value of x? Careful. I know you're tempted to say x, but you need something here. For example, if x is -3, this ends up being +3. Absolute value. So to be a stickler about it, all right, the square root of the square of blah is the absolute value of blah. That's a nice thing to note. It shows you really know your stuff. It's the absolute value of blah over the square root of, hey, what's 1 minus cosine square theta? Says Mr. Pythagoras. 1 minus cosine square theta is sine square theta. And you can see that it's gelling, it's coming together. We're getting something that looks a lot like that. All right. But now, wait a minute. You might be asking, how come we're removing the absolute value on the top? By what right do we have to do that? I'll give you some hints. What's the absolute value of 3? It's 3. What's the absolute value of pi? It's pi. What's the absolute value of 0? It's 0. That's all cool. But what's the absolute value of -3? The absolute value of -3 is +3. All right. So what's the idea here? Look at the first three examples. If you're taking the absolute value of a non-negative value, the output equals the input, right? These match up. The only time you don't get a matchup is if the argument here for absolute value is negative in value. Anyway, a couple of points here. I claim that 1 minus cosine of theta is always non-negative for all real values of theta. And it's good to write these comments here. Why is that? If I have $1 and you take away cosine of theta away from me, how much can you take away from me? Well, cosine of theta could be -1. Maybe you're giving me $1, right? But it's a range issue. The range of cosine of theta goes from -1 to +1, all right? But the highest cosine of theta can be is +1. So if I have $1 and you demand cosine of theta from me, then at most I give you the $1. I'm not in your debt or anything. All right. At most I give you $1. 1 is the highest number in the range for cosine. All right. So wait a minute. I have $1. You're taking away cosine of theta from me. Then that means that I have non-negative amount of dollars. I'm not going to be in debt to you. All right. So because of this range observation, you should agree with me that 1 minus cosine of theta is always non-negative for all real values of theta. That means that I can and I should remove absolute value. That's a simplifying step. For example, you don't want to give a final answer where you have absolute value of 3 as a part. You would want to simplify that and just write 3 in its place. So where possible, you are expected to remove absolute value appropriately. Okay. Anyway, so we have 1 minus cosine of theta all alone on top. That's good over here. Once again, by this rule over here in red, the square root of x squared is the absolute value of x in general for real values of x. Likewise, the square root of sine squared theta is going to be the absolute value of sine of theta. But this time, we need the absolute value symbols because sine of theta can be what? For some real values of theta. Sine of theta can be negative, right? Sine of theta can be negative, which means I need to leave the absolute value. If you're taking the absolute value of something that could be negative, you better leave them on. Anyway, QED. Now, why are we doing this? This leads to some of the half angle identities for tangent. It's like 16, 17, and 18. How do you get from 16 to 17 or 16 to, 17, 18, 19? How do you get from 17 to 18 and 17 to 19? They're related to the trig identities. Can I pull them up quickly here? Yeah, advanced identities. Yeah. Remember? Number 17, number 18, number 19. Oh, what we're doing is it is this guy. Yeah. So we're basically showing why we get this over here. And the thing is, it so happens that sine of theta has the same sign, SIGN, as this guy, unless you have a quadrantal issue or something. So it wasn't clear. It wasn't as clear why you can remove absolute value here. All right. Here, I'm fine with you just stopping right here because it's not super clear why sine of theta has the same sign SIGN as tangent of half theta. If you play with quadrants, you'll get a better sense of why. All right. Any questions about that? I'm sure a lot of students were wondering about that. Any questions about that? Okay, so we're digging along. Okay, so I have 814 right now. All right. So we did 5-2. Okay, now where are we? 521E. Is it the same when doing number 8? What is 8? Number 8.
They're asking about in 6.3
6.
when you did 7.
Oh, yeah. Oh, and that's kind of a trick question. Okay, see, here, this vector is 5 times this vector. This is -5 times this vector. So here's the thing. These two vectors are parallel, but They actually don't have the same direction. They have what directions? It's not the same direction. It's what directions? This vector is -5 times this
Opposite.
vector. Yes, correct. Opposite. If the multiplier is negative, this is pointing the opposite direction from this. So they're parallel, but they're not pointing in the same direction. I was asking, are they pointing in the same direction? Answer is no. They're parallel, but they are not pointing in the same direction. That was trickier. Very good. Okay. Okay, anyway, we're going to do some 5-5 problems next, it appears. So, where are we? Okay, so I have 8:16. I have no sense of time. Okay, 8:16 p.m. All right, so let's break until 8:27 and we shall reconvene. So let's reconvene 8:27. Can you see all this mess here? Break until 8:27. All right, I'm going to remember to unmute and record. I'm going to mute and pause now. Okay. Remember, Jeffrey Tubin got fired because he didn't mute stuff, right? So be careful.
Oh no.
Yeah, that guy got fired. He just got fired from the New Yorker. That's a news item.
Well, wasn't it? Didn't he have the video on, not the audio?
It was video. I'll not go further into that. It was video.
Yeah, I know.
Recording that. All right. So, okay. Now, again, correct me if I'm wrong, but I believe we're at 5.5 here. 9 ABC and 12A. Okay. I think I have panels for some of these. 5.5 and 5.4 are the same one, by the way.
Yeah, actually, I asked for those, and I actually just realized I did 9A. But I do not know how to start 9B.
9B. Okay. And if anyone wants to jump in and if anyone wants to see those, I think I may have some panels on some of those. But let's go over here. All right. Okay, so your first inquiry is 9B. So let's go to the last section of chapter 5. 9B. Oh, yes. I remember I worked with someone on this today, I believe. So I think I have some notes on this. Yeah, I have some notes on this. So let me refer to those notes. 5.2. Wait, 5.4. This is 5.4 9B. 5.4 9B. Here we go. There we go. Okay, in its full glory. All right. Okay. Now I could do the Socratic method, but hey, I got the solution here. Let's go over it. Okay, let's be efficient. All right, so 9B. All right, so I rewrote it here. We can start from scratch. I rewrote it here. Okay. Now the key thing is you want an identity for cosine of 2x. So you're looking for a double angle identity for cosine. Now the thing is, you have a choice. We have 3 of them, right? Now the classic one goes cosine squared x minus, because the plus case gives you 1, right? Cosine squared x minus sine squared x. But the form that's most useful is this version, where cosine of 2x equals 2 cosine squared x minus 1. Because notice here we have a cosine of x term. So we'd like to keep things in terms of powers of cosine of x. Now, you could do this, but then you're going to basically rederive this because you're going to want to apply a Pythagorean identity to this guy over here. And it's okay to immediately replace this with this. I assume that this is an identity that you know or should know, okay? This is one of 3 versions of the double angle identity for cosine. We may as well use this because there's no sine in here, right? Okay, so directly, this is like number 10 or 11 or something, but cosine of 2x I'm replacing with 2 cosine squared x minus 1. You might want to start by considering grouping symbols, but since this is at the beginning, you don't need the grouping symbols, so we can ignore them. All right, plus 3 cosine of x plus 2 equals 0. All right. 2 cosine squared x plus 3 cosine of x. We combine the -1 and the +2. We get +1 equals 0. And then I'd recommend a substitution. You don't have to, but I recommend a substitution. Any questions thus far? Any questions thus far? Feel free to unmute and say something if you have an oral question. Any questions? I would recommend a substitution. Let u equal cosine of x, and we have this cutie in u, this quadratic trinomial in u. 2u squared plus 3u plus 1 equals 0. You could use the quadratic formula, but old school factoring does work. I should hope so. I'd have to be in a really bad mood for old school factoring to not work on this kind of problem. All right, but the old school factoring works. 2u squared breaks up as 2u times u, or vice versa. Both same sign, both positive. It's got to be +1, right? If it's going to work. Okay, and this does work out. For example, notice that +2u plus +1u is +3u. So this is the factorization for that cutie. Questions thus far? So the tricky part so far, identifying the best trig identity, which version of the double angle identity for cosine, and also some factoring over here, factoring cuties. It's always a challenge to factor cuties. All right. By the zero factor property, you set each factor equal to 0. All right. So we're still in the algebraic phase. Solve for u. And I assume that you can solve these linear guys in your head. So you can just write from here, u equals -1/2, and then u equals -1. And that pretty much ends the algebra phase of this problem. Now we go to the trig phase, right? Who was u? Sounds like bad grammar, but who was u? U was cosine of x. So we have cosine of x equals -1/2, or cosine of x equals -1. I'll pause here. Any questions thus far? I'll give you a moment to let this sink in. All right, all sunk in. You believe me up to these basic cosine equations, but don't rush them. All right, draw that unit circle. I strongly advise you draw that unit circle. Okay, this guy's easy. Let's do this guy first. This guy's easy.
I got the rest of the problem if you don't want to proceed with it. I just made a mistake. I made a mistake. I was doing the wrong identity on it, on that algebra part.
Did you use this here?
Well, I didn't use that one. I was using the other ones for some reason. I don't know why, and that's why I couldn't get the answer.
Well, that's okay, because let me show you. Because remember, you can derive this from this, from the big daddy for cosine of 2x. Here's a way to look at it. In fact, as a student, I might have done it this way because I was more familiar with that original identity. Okay, so the way to derive it, by the way, to get from here, let's see, to get from here to here, all right, by Pythagorean, it's the cosine, cosine squared x minus, careful, you got to group it, right? Sine squared of x is 1 minus cosine squared of x. Basically, cosine squared x plus cosine squared x is 2 cosine squared x minus 1. So you can derive this from a Pythagorean. Okay, and then so on and so forth. And just for students' benefit, I'll quickly go over this. So cosine of x equals -1, all right? That corresponds to West Point, right? That's where the horizontal coordinate is -1. Careful, x here is an angle. Cosine of x is just the horizontal coordinate here, right? Okay, so pi is the most famous angle. So that corresponds to x equals pi. We want all the coterminal twins. So we want pi plus 2 pi n. A lot of students have trouble writing that though, right? But the thing is, see, some students write pi n. But the problem with that is that picks up all of these guys and also all of these guys. So that's not what we want. Some students just write 2 pi n, but that's not right because that only picks up east point. If you only want west point, you want something like x equals pi plus 2 pi n. But a lot of students don't feel comfortable with this. Bear in mind that this or this would be inappropriate. For one thing, we don't want east point. You don't want to pick up east point. This is one of the few ways you don't pick up east point, right? And over here, cosine of x equals negative 1/2. It might help to know what the inverse cosine of positive 1/2 is. That's pi over 3, the reference angle. That's not a solution, but it's the reference angle for all the solutions. His nice brother here is 2 pi over 3. His nice brother here is either 4 pi over 3 or negative 2 pi over 3, right? Going clockwise. If you want all real solutions, you can pick either. This might be easier for you because then you can write the set of all x in the reals such that x equals plus or minus 2 pi over 3 plus 2 pi n, the coterminals, and then these guys in black over here. Although later on, when I ask you for the solutions between 0 and 2 pi, what are the solutions between 0 and 2 pi? The solutions between 0 and 2 pi are, I think the first one is 2 pi over 3, and then pi, and then 4 pi over 3. You don't have to order them, but if you want to walk around the unit circle, remember, pi over 3 is not a solution itself. It's a reference angle. It's 2 pi over 3, then pi, then 4 pi over 3. For 9b. Or did I just want all the... Five, 4, 5, 5, 9b. Yeah. I asked for the general solution set for, so what I have here written first, that's the nice typeset version of my messy work over here. My messy handwriting here, here's this in nice typeset, all right? And again, the solutions between 0 and 2 pi, I said them, 2 pi over 3 in quadrant 2, also pi over here, quadrantal, 4 pi over 3 in quadrant 3. All right. Questions? Yeah, some good solid problems here. Definitely show work. Don't give answer only. You got to show some work. Basically what I have here, although you don't necessarily have to draw the unit circles, but I still recommend them. All right, any questions about this? All right, any questions? Okay, so let's see.
Yeah, so for 9C,
9C?
I got pi over 3 and 5 pi over 3, but I just don't understand how pi and 0 are in the solution set.
All right, so 9C. 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 5, 4, 9C. Over here. 5, 4, 9C. This one. This one? Is it this one?
Yeah, it's
Yeah.
this one.
Okay, deceptively easy looking, but you have to think a bit on this one. All right, so sine of 2x equals sine of x. I knew you're tempted to do so much. 2x equals x? No, sorry. Sine of 2x expanded. We have the double angle identity. We get 2 sine of x cosine of x equals sine of x. Now, a lot of students are tempted to divide by sine of x on both sides. I don't advise that.
That's
now,
what I did.
now, in Math 255, that is a trick you use, but here's the thing. You have to consider the case where sine of x is 0, right? So that's the problem.
Yeah.
If you divide both sides by sine of x, you must consider sine of x equals 0 as another branch, right? Because when sine of x equals 0, this works out, 0 equals 0. But so many students forget that instead of dividing by sine of x, I advise that you subtract. Subtraction is much safer. It's very rare. You don't mess up subtraction, okay? Subtract sine of x from both sides, then factor, okay? And this is a reminder, hey, sine of x equals 0 gives us solutions potentially, and it does here. And then you set this equal to 0. Basically, you get cosine of x equals 1/2, and you get two fairly basic trig equations. I could proceed, and if anyone wants to, I can. But if you get up to here, I think you're in pretty good shape. But if anyone wants me to complete this, I will. Work shown. Yeah. I was mentioning that before on B. Let me bring back B. For something like this, yeah, basically show all this work. You don't necessarily have to substitute, but I think that saves you time. You don't have to do this stuff over here. I was rederiving the identity, right? But the stuff I have in blue here, I recommend a substitution. Show me the factoring or the QF. Show me the factoring or use the QF. All right. You don't have to draw the circles here, but I do recommend it. All right.
Someone asked if he can complete it.
Yeah, sure. Anyway, that was the work question. Now going on to C, let's complete. Good practice. All right. So, all right. From the zero factor part, first of all, you agree that we're good up to here, right? You agree we're good up to here. Double angle identity, subtract sine of x. That's a lot safer than dividing, okay? Because you're in danger of losing solutions when you divide. Factor, again, that tends to be safe, right? Now, from the zero factor property, our old friend, we set each factor equal to 0. All right, so that's where we start. Let's restart this. All right. All right, here we go. So we have now, okay, it's in black, that's okay. Sine of x equals 0 or 2 cosine of x minus 1 equals 0. Bottom line, you add 1, divide by 2, cosine of x equals 1/2. You can do that fast. All right. Now let's look at the unit circle. You don't have to draw it, but I highly recommend the unit circle. I couldn't do trig without the unit circle. All right, sine of x equals 0. Now don't get confused. X is at the angle here, but sine of x is going to correspond to, it's kind of like the y coordinate on the circle, the vertical coordinate. Where is the vertical coordinate? 0. We want, put this in burgundy. We want, again, look at this, east point and west point. East point and west point, right? So what are some sample angles? Well, 0 here, pi here, 2 pi here. Also, they're opposites and so forth. Now, you don't have to write this on your work, but I encourage you. Look, as students, you want to learn, right? You want to keep your knowledge. And I encourage you to draw these circles for your future knowledge, whether or not I grade on them. All right, anyway. So what's a succinct way of... Now, you might be looking, am I going to get an overall symmetry? We'd have to be really lucky. I don't think we do. Yeah. So I don't think there's an overall symmetry. I'm going to do it case by case. All right. So the set of all, whoops. 1 second. All right. The set of all x in the reals such that x is of the form pi n, any integer multiple of pi, like 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, etc., and their opposites. And before we forget, where n is integer, it's a safe bet you're going to need that at some point, these problems. Or, all right, well, 1/2 is very much in the range of cosine. It's a special value, so we're going to get some special angles here. All right, let's see, go back to black here. In what two quadrants is cosine positive? Think horizontal coordinate. X is technically the angle, but it's like the x coordinate on the circle, the horizontal coordinate on the circle in quadrants 1 and 4. The horizontal is positive. All right. Now, cosine of x equals 1/2. That's actually the steep guy here, right? High and to the left, the hippie point. High and to the left. And what is the angle we normally associate? Also in the brother over here, right? Brothers. So what are the angles we associate here? Up here, it's the steep guy, right? High and to the left. Pi over 3. That's the reference angle for this branch of solutions. And it's also a solution itself, right? Also, now again, over here you have a choice. For all real solutions, the quick and dirty way is to just say, hey, negative pi over 3. And then if we're dealing with the angles from 0 to 2 pi, we can deal with the positive brother, twin. All right. Anyway, or if you want to get done with this quickly, or x can be of the form. That's a pi, by the way. That's a horrible pi. All right. X equals plus or minus. That's very succinct. Plus or minus pi over 3 plus 2 pi n. Still, we want all the coterminal twins. Where n is integer. And I hope that's the general solution for 9c. Am I getting my own answers right? There we go. Yeah. X equals pi n, or x equals plus or minus pi over 3 plus 2 pi n. I'm going to lead as well. I would like a fraction bar here. There we go. And then going around the world, what are the solutions? Okay, so that's all real solutions. That's for all real solutions. Now on the interval from 0 to 2 pi, let's go around the world. Okay, so in blue, I'll mark the angles we get going around the world. Hey, 0. At the starting gate, 0. We go around, we get pi over 3. We go around, we get pi. You don't have to do these in order, but I like the idea of going around the world. Okay, now, for this point here, we don't want negative pi over 3. We want his smallest non-negative coterminal twin. What pi over 3? Twice 3 is 6. 1 less than twice 6. Sorry. Okay. Twice 3 is 6. 1 less than 6 is 5. 5 is 1 less than twice 3. 5 is 1 less than twice 3. All right, so I want that guy there. So 0, pi over 3, pi, 5 pi over 3. You don't have to order them, but I think that's a nice little idea going around the world. For C, yes, 0, pi over 3, pi, and 5 pi over 3. The only 4 solutions between 0 and 2 pi. All right. Any questions about this? Again, a nice solid one. All right. Okay, so let's see. We've done 9b, we've done 9c. For 9a, I have a panel on that. Nine A.
Oh, that's the one that I said I actually did. If you don't,
Yeah.
But unless if anyone else wants it.
Yeah, but I'd like to. I can quickly review it. It's 5, 4, 9 A. I know I have a panel for that one. 9 part 1. That looks like it's it. Yeah. Let me label it A. Yeah. There we go. You sunk my battleship. Yeah. All right. Here we go. To start people off, right? Because I know it's kind of funky looking, right? Because you look at this and you go, 4 sine of x cosine of x. Well, what am I going to do with that? It would be great if we had to put a number in front. How about a 2, right? Because that gives us an identity. Well, 4 is 2 times 2. And you know what? For some of you, that might be all you need. Remember that basic arithmetic fact. 4 is 2 times 2. And 2 sine of x cosine of x is sine of 2x. And then this 2 is this loose piece that's hanging out there, right? Add 1 to both sides. We get sine of 2x equals 1/2. Now, remember, we just used the double angle identity. Don't unravel it. It's now a multiple angle problem. I would recommend letting theta or u be 2x and proceeding from there. Don't forget to go back from u to x, though. All right. So 5, 5, 9, ABC. What about 12a? Where are you at 12a?
For 12a, I don't know how to start that one.
Let me see which problem it is. Oh, yeah, yeah. So just in general, how do you apply these things, right? Because I didn't discuss the derivation of these identities. I just wanted people to use them as they see them. Okay, so I'm going to need my notes then, because I haven't even had these memorized myself. To be frank, I don't really have a particular need to. I mean, I don't feel too guilty about not really knowing these myself. All right, so product of some identities. Okay, and these are good, by the way, in calculus, because remember, calculus likes sums and differences, not so much products or quotients. All right, so 12a, just to get you started, right? Let's get a new sheet, because this is my first one. New sheet. All right. Okay. Let's do brown. Let's do brown. All right. 12a. Cosine of 3 theta times cosine of 5 theta. Okay. And then once you get the hang of it, it's pretty good. And remember, you're totally allowed to use the identities in my this is a separate handout technically. It's also part of my 5455 file, but you can find this somewhere. And it's at the end. You don't have to memorize these. You're never expected to memorize these. Product of some.
Oh, okay. I didn't see these identities, so that's why I was kind of lost on this one.
Yeah. Have you seen this handout? Do you know what I mean by the handout? This handout?
Yeah, I've seen it, but I didn't see those.
Yeah, because I rarely refer to them. I rarely refer to them. Yeah.
Okay.
So it's a matter of applying them. Can you apply these identities properly? So it was what? Okay, so this is, first of all, it's 12a. All right. Okay, so 5455 12a. Okay, let's get us started. Okay, so it was cosine of 3 theta, cosine of 5 theta. Calculus goes, yuck. I don't really like to differentiate that, and I don't even know how to start integrating that. So that's why you use the product of some identities. So the idea is on an exam, for example, I would give people this block. They choose the appropriate one. Well, we have a product of cosine guys, right? Where u is 3 theta, v is 5 theta. But in fact, because of commutativity, you can even switch these and it doesn't matter. That's because cosine's even in particular. All right, anyway, so following this identity, all right, equals 1/2 times the quantity. And then you would plug in u equals 3 theta and v equals 5 theta. Cosine of 3 theta minus 5 theta plus, because calculus likes sums and differences, cosine of 3 theta plus 5 theta. All right, equals 1/2 all times cosine of 3 theta minus 5 theta is negative 2 theta. By the way, don't forget to cross your thetas. A lot of students get sloppy with that. Plus cosine of, what's 3 theta plus 5 theta? It is 8 theta. Again, it's 8 theta, not 80. Please cross your thetas. A lot of students get lazy, just do that. Cross it. All right. Come on, it's a stroke. Now, the thing is, though, we know that cosine is what? Even or odd?
Even.
Even. This guy dies. So we can simplify it a bit more. Equals 1/2 times the quantity, cosine of positive 2 theta. That's generally preferred. Plus cosine of 8 theta. Now, do you want to know the trick at this point? The trick at this point is to stop. Stop. Because, and students have lost maybe a point or two because of this. This is not cosine of 10 theta. We don't have that. I know you're itching to say that this is cosine of 10 theta, but no. It's like square roots or logs, right? There's nothing that says that a sum of cosines equals cosine of the sum. We have nothing that says that, okay? So know that you stop here and don't try to go too far and be wrong. You stop here. If you want to distribute the 1/2, be my guest. All right. I might have even accepted the negative sign there. Depends on the wording of my problem. And it is in my answer sheet, right? How come it's over here? Yeah. 1/2 times the quantity cosine of theta plus cosine of 8 theta. And I gave people the hint that you may start with negative 2 theta at first, but then cosine's even. Okay. Questions? Questions? So you would apply the product of some identities like so. Sum to product. These are good for solving equations because we like products for equations. Product equals 0, right? So you pick the right one, apply. Don't go too far. Questions? Questions? Okay. I think we're okay there. Okay, 6.4, the 14 and 15. 14 and 15. Save this. So I can come back to this. Okay, 6.4, 14 and 15. Yeah, those don't sound familiar. Yeah. Okay, yeah, and students always ask me about these as well. Okay, so in fact, I'm going to mark up the primary homework sheet. I'll still circle these just for my reference. 14 and 15. All right. Prove that equals that. Oh my gosh, prove. Don't worry, it's basically a plugin. So the way that you'd start this is as follows. Maybe I should do a separate sheet for this. I like having separate sheets. Let me do a separate sheet. Again in brown. Okay. That's in brown. And I'll make the label in brown also. Okay, so this is what, 6.4, number 14 and 15? Okay, now let me say this. 14, I'll show you this. Now 15, it's a matter of plugging into this formula. So when I say find the component of W log V, and by the way, you don't even have to know what that is. That's a physics idea you can look at the notes for under work. But the main thing is on 15, you basically work this expression. You take the dot product of the two vectors, divide by the length of V. And we can go over that as necessary. But 14, it's a matter of, it's right there in the notes, right? The formula from the notes, where is that? I gotta get out again. 6.4. It was this guy again. Yeah. This formula for cosine of theta, the dot product over the product of the lengths, you plug in here. All right. So what's the deal? On number 14, the deal is component, which is a scalar itself. It's a scalar divided by a scalar. This guy's a scalar. The component of W along V. Just to give you an idea, if this is the W vector and this is the V vector, the projection of the W vector looks like this. Oops. The component is like the signed length of this vector here. So it's like, what's the relevant aspect of force in this direction if we move a block up an incline? All right. If the arrow's going this way, then the component is negative. Yeah. All right. Anyway, the component of W along V, which is the length of this projection guy here, in case you're curious, that's equal to, now I'm telling you it's the length of W times cosine of theta. And that's from a SOHCAHTOA relationship, right? What relates this angle here with the adjacent side and the hypotenuse? Cosine. It's a cosine relationship. All right. And then how do we get this formula? You use the formula for cosine of theta over here. So it was a matter of referring to the notes. Cosine of theta is, that's a small times, the dot product of the two vectors over the product of the lengths. And what happens? we assume that these vectors are non-zero, right? What happens? Boom, boom. This divided by this is 1. And we're left with, voila, this guy over here. The dot product over the magnitude of V. So it was a matter of comfortably plugging in this formula for cosine of theta. Okay, so it looks like a bit of a mess, but algebraically it makes sense. It's just that this dense notation makes people kind of nervous. It's more a matter of nerves. This is 6414. All right, questions about that? Any questions? And 15, again, you want to take the dot product, put it on top, take the length of V, put it on the bottom. So I'll give those two as key hints. And if you want me to work 15, then we can do 15. Okay, so let me know. Okay. 6.3, 5 ABC. Yeah, in the videos I did almost all 5 problems except for these 2. So chapter 6 is still pretty much open territory right now. All right, so this is 635, which I've not done yet, I don't think. So let's do it. Okay, as we get past 9 p.m. Okay, I'm getting a whiteboard, right? That's what I'm doing. Why am I on the screen? Why am I in the kitchen? All right. 635. Ah, yes, yes. And someone asked me about this before as well. So let me do a quick recap here. So let's do a recap. First of all, the vector v, you can think of this as, I'll do this in blue, maybe, the additional notes. All right. So the negative 2i plus 5j, that's a physics way of looking at it. You might feel more comfortable writing it as angle brackets, negative 2, comma 5. You might feel more comfortable with that. I personally do as well. But I wanted people to know this also. Part A, find the unit vector in the direction of V. All right, so this gives a vector V. It looks like it's going northwest, going through quadrant 2 as a position vector. All right. All right, find the unit vector in the direction of V. Write it in XY component form. Give an exact answer, don't approximate. Rationalize denominators. All right, so the length of this vector turns out to be greater than 1. I want to normalize this vector. I want to find the vector of length 1 that points in the same direction. There's not the scale, but I want the vector of length 1 that points in the same direction. Again, that's called normalizing a vector. And this process is great for, well, we like unit vectors in proofs, in vector proofs, right? You can think of this as a pointer on your compass, right? So that if I know I'm dealing with a unit vector, then the only thing I care about is the direction. All right. We know it already has length 1. So for part A, here's how I'll start you off. I like to call the unit vector u. U is given by the vector v, which I'll call negative 2 comma 5, that guy here, right? Negative 2 comma 5, divided by the square root of this guy squared plus this guy squared. So I'll write like this, shorthand. This guy squared is Pythagorean, plus this guy squared. And then I tell you to rationalize denominators, all right? And then bring it inside there. I guess I may as well work it out. Maybe I should do. In case people want to see it. Yeah. I'll just do this here then. Okay, so this is 6-3, number 5. All right, and then which one is this? This is oops. Oh, wait. It's this one here. Okay, so this is 6.3, number 5. Okay. So I'm going to copy my notes here. Interject if you have any questions. Okay, so again, we want to normalize the vectors. So we have u equals the original vector divided by the length. Okay, which is -2 comma 5, basically, in angle brackets, over the square root of the square of -2 plus the square of 5. Okay, good. I'm recording. I would have cried if I weren't recording. Equals. All right. So we have -2 comma 5 over square root. Bottom line, 4 plus 25 is 29. But I need to do a couple things. Okay, now first of all, let's bring them in. Okay, this is scalar division. So we have angle brackets -2 over root 29, comma 5 over root 29. When you divide a vector by a scalar, you divide each component by the scalar, non-zero. But we're not done yet still, because we give an exact answer and rationalize denominators. These are rationalizable. Okay, so what do we end up with? You don't have to show the work for this, but for the rationalizing. I believe it when you say it's -2 root 29 over 29, comma 5 root 29 over 29. And angle bracket. If you don't believe me, we can go over that, but we're basically multiplying by root 29 over root 29, right? The purpose, that's the vector of length 1, the unit vector, the compass pointer or needle, right, in the same direction as the given vector. Normalizing. By the way, this also comes up in directional derivatives. You want to know the directional derivative as you climb a mountain, right? How steep are you climbing? What's the directional derivative if your compass has radius 1 inch or whatever, right? And you get this unit vector as your compass needle. Okay, and you can do a bunch of computations. What's the directional derivative and all that? Whew, okay. That was 5. 5a. Okay, now 5b. Find the direction angle of v. That comes from a formula. Can I do b here? Different color? Blue. Whoops. Oh, yeah, that's right. Do this. All right, so what about part B? That comes from a formula. From the notes, it was 6-3. Here we go. See that picture? Tangent of theta, SOHCAHTOA. Tangent of theta is opposite over adjacent. Tangent of theta is B over A. Watch your quadrant, though. All right, so part B, handy dandy formula. Okay, and what are B and A? A is -2, B is 5. We sometimes prefer those to x and y because a and b more represent constants, right? So a is -2, b is 5. Yes, this sounds familiar. Yeah. Equals -5 over 2 or -5/2. All right. But wait, we're not done. We want the actual angle. All right. Now we see from here, even from the original vector, right? V and u point in the same direction, right? Because we're dividing by a positive real number here. V and u point in the same direction. That was the whole idea, right? Now, -2 comma 5, that points in the northwesterly direction. Okay, -2 comma 5. Oh, yeah. Okay, -2. Now, the vector v is -2 comma 5, but this is a unit circle. So actually, this is going to be u. This is the u vector, actually. It goes like this. -2 comma 5. Something like that. All right. So tangent of theta is -5/2. Tangent is negative. All right. So you might be thinking, well, hey, wait a minute. Then this should be very straightforward because you might be thinking, oh, so if I just take the inverse tangent of -5/2, I should be okay. Well, let's think about this. Let's think about this. What is the range of inverse tangent? What are the angles we pick up for inverse tangent outputs? Well, tangent of -π/2 and π/2 are undefined, but we pick up all angles in the middle. That's that key interval of interest there. All right. Now, if you work out inverse tangent of -5/2, get a calculator. Get a calculator, and remember, in Chapter 6, we normally do degree mode. What's that in degrees? The inverse tangent of -5/2. -5/2 is a tangent value. Every real number is. I have to get my own calculator. All right, here we go. What are you getting? What are you getting? To the nearest, what, 10th or so? Is it 10th? Yeah, nearest 10th of a degree. All right. So what is this to the nearest 10th of a degree? Let's see here. Inverse tangent of -5/2. And I want degree mode. Remember that brain meme? It was in radian. Go to degrees. I'm getting -68.2 degrees. I got two problems with that response. If a student tries to pass that off as an answer, I have two issues with this answer, and one is more serious than the other. Right. So to the nearest 10th, -68.2 degrees. I have two problems with that answer. One of them is much more serious than the other as a practical matter. What are two problems I have with that answer? Again, look at the statement of the problem. And look at the pictures I have here. What are the two issues I have with this? And again, one is much more serious than the other if you want to dig for your tickets. Issue number one. A direction angle has to be between 0 degrees and 360 degrees, right? This is outside that interval. But that's the least of it. There's another huge problem. What quadrant is this purple angle in? That inverse tangent result. What quadrant is negative 68.2 degrees in?
Fourth.
Correct. You're not getting this angle. You're getting this angle. You're going in the wrong direction. If you want those tickets, you're going in the wrong direction. The exact opposite of what you want. How many degrees do you add to get back up to the direction you do want?
180.
Correct. You want to do a flip-flop. You add 180 degrees. The unit circle tells us so. So what happens when you do that? When you add 180 degrees, you get 111.8 degrees. Is that right? My arithmetic stinks in real time. 5. Oh, am I right? 111.8 degrees. Yes, that's the answer. The direction angle is that. A nice quadrant 2 obtuse angle corresponding to this turquoise arrow. By the way, this is the unit vector u. It's not the vector v. If this is the unit circle, this is the unit vector u. Which is fine because v and u point in the same direction anyway. Okay. So they might be asking, so wait, when do I add 180? When do I add 360 degrees? Draw the picture. Draw the picture. Watch your quadrant. Okay, and then C. Find the vector of magnitude 4 in the direction of V. Okay, I'm going to make this very quick here. In part A, you found a vector u, the unit vector that pointed in the same direction as the vector v over here. How do you find a vector of magnitude 4 that points in the same direction of v? You take the unit vector and you just multiply by 4. That's all you do. That's another reason why we like that why we like that unit vector. Why do we like unit vectors? Why do we? Because they're used in a lot of proofs. Because it's like a standardized compass needle, for example. And we can easily construct vectors of certain lengths that point in the same direction. If I want a vector of length 400 that points in the direction of v, I want 400u, and so forth. So it's a nice building block. All right, so that's 5, I believe. 635. Any questions? Any questions? All right. Um, 5, 5, 11. That sounds new. Ah, yes. All right. I had several requests for this one. Let's do it. Okay. And then after this, I'm going to need like a 5-minute break, definitely. So, all right. So let's do 5, 4, 5, 5, 11, and then I'll take a 5-minute break and I'll come back for some more. All right. Okay. I'm definitely going to need 2 or 3 of these whiteboards. All right. Green. Okay. Green. All righty then. You're in calculus 2. All right. In the future, you're in calculus 2. You're told to integrate cosine of the 4th x. You basically have to get a form like this because in calculus, integration like something like this, where you because integration, calculus hates squares. Calculus hates fourth powers even more. All right. But if you can break this down like this, calculus likes guys like this, Numbers in front, no problem. Calculus really likes something like that. So let's do it. All right. And remember, you can check on Desmos if you don't have my answer. Cosine the fourth x. Oh, I just realized. I just started. Yeah, I already started somewhere else, but okay. Well, I don't have an identity for cosine of the fourth x. I do have an identity for cosine squared of x. How's cosine of the fourth x related to cosine squared x? It's a square. All right. Now, apply a PRI, power reducing identity. All right, let's do that. Let's go to purple. Equals square. And then you might want to look at your, now folks, you really should commit these PRIs to memory because we often do use these. All right. For cosine squared of x, remember, sin is bad. Sine corresponds to the minus guy. For cosine, we have a plus sign. 1 plus cosine of 2x all over 2. Movies. There we go. Okay, finally. All right. Now, how do you square a fraction? You square the top, square the bottom. On the top, we have the square, of 1 plus cosine of 2x. On the bottom, square of 2 is 4. All right. I'm going to factor this out as a 1/4, not a 4, a 1/4. All right. Let's square the top. Is it 1 plus cosine squared x? Or cosine squared 2x? Either way, no. Either way, no. Why not? Square a plus b. What is a plus b all squared? It's not a squared plus b squared. In general, it's a squared plus 2ab plus b squared. All right. So what am I getting at here? A lot of students forget this term here. You want twice the product of the two terms. 2 cosine of 2x. That's twice 1 times cosine of 2x. All right. Any questions thus far? Any questions thus far? What shall we do now? I have different ideas here. We could even distribute now, actually. Maybe that would help. Equals, Let's try distributing the 1/4. I don't think I've done that before, but let's try that. 1/4 times 1 is 1/4. Plus 1/4 times 2 is 2/4 or 1/2. And cosine of 2x. All right. Plus 1/4. Don't forget the 1/4. Times, I would go to the next line. All right. 1/4 from here. 1/4 cosine squared of 2x. All right. Okay, so far so good. Question so far. Question so far. Check this out. We better use the PRI again. But this time, you have 2x as the argument instead of just plain old x. All right. Any questions so far? Questions so far? Okay, now, guess what? PRI again, so let's do it. Okay, so now we have equals 1/4 plus 1/2 cosine of 2x plus 1/4 cosine squared of 2x. So how does it work? 1 plus cosine of twice the argument all over 2. One plus cosine of, well, wait a minute. What's twice 2x? Twice 2x is 4x. So we're doubling that argument twice all over the 2. So again, cosine squared of 2x is 1 plus cosine of twice 2x all over 2. Question so far? Question so far? And then it's a matter of being careful with your pre-algebra. 1/4, whoops. 1/4 plus 1/2 cosine of 2x plus, how about this? We multiply the fractions down here. 4 times 2 is 8. All right. And then we break the fraction up because we need these nice, elegant pieces here. Breaking up the breaking up into 3 unlike terms. Okay, so we have 1/4 plus 1/2 cosine of 2x plus, break the fraction, 1/8 plus 1/8 cosine of 4x. So cosine of 4x is in the mix. Why? Because we applied the PRI twice. See, here's the thing, folks. Notice when we go from here to here, we have the benefit of killing the square, which calculus loves doing. One price we pay, though, is that we may make the argument worse. So we double the argument. That's what's happening here. Here we go all the way to 4x. All right. Finally, I think we're just one step away, really. What's 1/4 plus 1/8? What is 1/4 plus 1/8, right? 2/4 plus, wait. 1/4 is 2/8. 2/8 plus 1/8 is 3/8, correct. And that was, 1 second. And those are the only 2 like terms we had to combine. 3/8 plus, okay, the coefficient here is 1/2. That's cosine of 2x plus coefficient here is 1/8. Is that correct? 1/8. Cosine of 4x. Did I get that right? 3/8, 1/2, and is it 1/8? Let me.
Yeah, that's right.
Is that right? Oh, good. I wasn't sure about the 1/8. Okay, so that's how you fill in the blanks. Right over here. 3/8, 1/2, 1/8. All right. And then in calculus, this is very easy to integrate. As it stands, you don't know how to integrate that until you tear it apart like so. And this is very easy to integrate and also differentiate. You'll see that. It's right. So, yeah, I'm very relieved. It could not have been. 9:30, good timing. I'd like to take a 10-minute break at this point, and then we'll continue on. All right. Any questions? I'd like to take a 10-minute break. And I'll see y'all at, how about 9:40? All right. I'll see you all at 9:40, and we will continue. Okay. If you've had enough, I don't blame you, but I'll hang on. All right, we'll look at the others. All right. Oh, it's right here. 940. Mu. Many of us have to go to the bathroom. Please. Please remind me to do that if I don't do that. But this is probably our final block. Okay, so this will be our last block here. All right. So where are we? Where are we? All right. Any questions about this? This was, yeah, and this is important for Calc 2, definitely. Number 11 on the 5455, right? That's the end of that. Any questions there? Okay, I don't know if I skipped anyone, but okay, okay, I see a private message, 6410. Let's see, which one was that? 6410. Wait, 6410. 64. Ah, yes, yes. These are concept problems, right? Okay, so all right, so 6410. What are the angles between basically V and 5V? So here's the thing. Let's say that this is a vector V. Oh, I should draw it a little bit smaller, actually. Let's say this is a vector V. What does 5V look like? What does 5V look like? 5V points in the same direction, but will be 5 times as long. What is the angle between these two vectors? If you have two non-zero vectors and they point in the same direction, what is the angle between them? The answer is 0 degrees. If you have two vectors, two non-zero vectors that point in the same direction, the angle between them is 0 degrees. All right. Now for part B, find the angle between V and W where W is the opposite of V. I'll do this in blue. Oh, okay. So here's the deal. So I'll copy this vector V. Let me copy him. All right. So here's our old friend, the vector V again. Whoops. Move him over here. All right. Here's the vector V again. And what does the opposite of V look like? What does that vector look like? That vector looks like this. Points in the opposite direction. So here's the opposite of V. What is the angle between these two vectors? Correct, 180 degrees. It's a flip-flop. They point in opposite directions. Finally, for part C, we're assuming these are non-zero vectors. V dot W equals 0. That means there, that O word, the vectors are orthogonal. What's a nicer word for orthogonal? Perpendicular. What is the angle between perpendicular vectors? Well, if this is V, this is W, right angle, 90 degrees. Question in chat. How can I show you the work? Well, I'd accept answer only, but for your benefit as a student, why not just draw little pictures like these, just to remind yourself why these make sense? Because this could help you on other problems, right? So I would accept answer only, but as for your reference, I would recommend you draw little pictures like these, little vectors, right? Like I've shown here, for your benefit. Okay. Um, do, 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 do. All right. So let's see here. Is this next 531 OPQ? Oh yes, good night. Yes. That's next, right? Okay. All right. So 5-3 OPQ. OPQ. There's a song that was kind of like that. Okay. Let's see. 5-3. Okay. 5-3. 1 O, P, and Q. Okay. And let me kind of scan over we just did 6, 4, 10. Okay, so and then the 2 over here. Okay, so let's do this. Well, 6, 4, 12, and 13. What were those? 6, 4, 12, and 13. What were those? Okay, so very quickly, let me address 12 and 13 quickly. Work on them, then I'll go to the 5-3 equations. Number 12 are the vectors 3, 7. Okay, I'm going to circle these. Number 12 and number 13 are the vectors 3, 7, and -7, 2 orthogonal. What do? Check the dot product. The question is their dot product equal to what number? What's that magic number? Is their dot product equal to 0? If the dot product is 0, they're orthogonal. If not, they're not. So that's the key. What real values for C will make the vectors orthogonal? Here's my hint. You're solving an equation, right? What's the dot product of these? Well, write down the dot product. It's a function of C, set that equal to 0, and solve. So my challenge to you is try to work that out. Find the dot product of these two vectors in terms of C, set that expression equal to 0, and solve. Set the dot product equal to 0 and solve for C. Okay, and then let me get back to you and see if you can get that, all right? Oh, wait. I don't think this person's still with us. Oh, no, with us, okay. All right. Let's see. I'm going to go back to the equations now. Okay, 5-3 OPQ. Let's go up to there. All right.
Yeah, I'm just having trouble finding the other values for O. Like I just don't understand how like I solved it algebraically and I got pi over 12, but I don't understand where like the other like 6 or 7 values come from
Which one? OP or Q?
for O.
For O. Okay, so let's start.
Well, basically all 3 of them.
Basically go alphabetically. Okay, yeah. All right. And we should have time for those because it's 9:48, and I think those are the last 3 in this list, unless anyone has anyone else. Anyone else has anything else? Okay, so OPQ. These could be our last ones. We'll see how it goes. I'll end at 10:30. All right. So OPQ. All right. I'm definitely gonna need a new whiteboard. All right. Let's see here. All right. Okay. All right. Let's go. How about green? How about green? Okay. All right. Oh. And this is section 5.310. 5.310. Yeah. And I know that I didn't do any OPQs before. So yeah, I didn't go to OP or Q. So I know this is new territory. All right. Oh, let's see here. 5.310. All right. Yeah, this is definitely a multiple angle problem. You're not going to use an identity. It's a multiple angle problem. All right. So I'll rewrite it. 2 cosine of 4x minus 1 equals 0. Solve for cosine of 4x, add 1, divide by 2. You do this in one step. Cosine of 4x equals positive 1/2. Okay? And then you're going to think of this as a multiple angle problem. So let's let either u or theta, let's see, either u or theta equals 4x. All right. Maybe u, because it's a substitution, so I might prefer u. All right, so let's go with u. Okay, so we have now cosine of u equals 1/2. Now solve this for u for now. Solve for u for now. But remember, you're not quite done after that. Solve for u for now. All right. Okay, so let's go to the unit circle. Again, in what two quadrants is cosine positive? That's the horizontal coordinate.
1 and 4.
1 and 4, correct? Now, the famous reference angle, and this will be a solution for u, that's going to be high and to the left, because 1/2 is 0.5. That's not as high as the other guys, right? Also, this point over here. What is the steep special angle here? The steep special angle is going to be pi over 3. And while we're at it, a convenient representative for this angle will be negative pi over 3. That might be helpful, right? Because we want to do both, right? We want to find both the all real solutions and the ones between 0 and 2 pi. Okay. So this could be helpful. So let's do that. I'll go ahead and write this in purple. Yeah, okay. All right. So we have then u equals, in fact, we can do it in one fell swoop. U equals plus or minus. This works. U equals plus or minus pi over 3 plus the coterminals 2 pi n. Where n is integer. I'll mention it once up here, then it carries through. But okay, now what is u? U is 4x. U is 4x. I'll put it in parentheses down here. You don't have to rewrite the whole thing if you remember that's 4x over here. All right. And then we want to divide both sides by 4. If you divide by 4, you're multiplying by what number? If you divide by 4, you're multiplying by 1/4. Now, on the left side, it's straightforward. 4x divided by 4 is x. Equals plus or minus. Now, this is where the 1/4 deal can help. 1/4 times pi over 3. Because you ask someone, what's pi over 3 all divided by 4? They might sheepishly say pi over 12, but they might be kind of wondering. Plus 1/4 times 2 pi n. All right. So then we have x equals plus or minus pi over 12 plus, and this is basically 1/2 pi n, or pi n over 2 or something like that, right? In fact, it's right there. I just spruce it up. The set of all x in the reals, the set of all x in the reals such that x equals this over here, n is integer. Hope that's right. Again, there may be different forms for the answer, but okay, so 5310. Yeah, that's right. X plus or minus pi over 12 plus pi n over 2 and is integer. Yeah, I'm kind of relieved. Okay, now in terms of getting, so I'm just going to go straight to my my answer sheet here. Okay, how do we pick up all the solutions between 0 and 2 pi? Oh, okay, yeah, maybe I will go to a new sheet. Yeah. All right, let's go to a new sheet. All right. We have two groups. I'll do the first in blue, the second in red. All right. Okay. We have two groups. Group 1. X equals positive pi over 12 plus pi over 2n. I'm going to factor that n out from the top, where n is integer. Here's the idea. We start with the case n equals 0, in which case we have pi over 12. So we start with pi over 12. Observe that if we try to subtract pi over 2, like n is negative 1, then what's going to happen is you're going to get a negative angle, and we don't want negative angles when we want the solution between 0 and 2 pi. Remember, we're trying to get the solution between 0 and 2 pi. So we don't want to subtract. Okay, we only want to add in group 1. All right, so what do we add? Well, the increment, where am I going to put that? The increment, what I call the increment, it's the coefficient on n, pi over 2. Pi over 2 is what over 12? 1/2 pi is what 12ths pi? Well, 1/2 is 6/12. So pi over 2 is equal to 6 pi over 12. That's what we keep adding. Pi over 2 plus 6 pi over 2, pi over 12 plus 6 pi over 12 is 7 pi over 12. 7 pi over 12 plus 6 pi over 12 is 13 pi over 12. Keep going. We're just a little past pi. 13 pi over 12 plus 6 pi over 12 is 19 pi over 12. Now, if you try to add 6 pi over 12 again, you're going to get 25 pi over 12. Notice that's a little bit over 2 pi. 2 pi is 24 pi over 12. So we're going to kill this off. All right. On an exam, I'd let people box these off, but technically you should put this in solution set form. And remember, they don't have to be ordered. They don't have to be sorted. So you can go ahead and list these 4 out. That's fine. And then in the second group, x equals negative pi over 12 plus pi over 2n. How about in green, actually? Well, where am I here? Red. Yeah, I'll go with red. Okay. All right. Group 2 in red. X equals negative pi over 12 plus pi over 2n, an integer. All right. So where do we start? Well, here's the idea. Okay, well, let's do this. Let's start tentatively at negative pi over 12. The increment is, again, pi over 2, which, again, is 6 pi over 12. I want a common denominator. But now look what happens here. We start with negative pi over 12. But wait a minute. We don't want him. He's too negative. He's like a bad friend. He's too negative. We're going to nix it. Bye-bye. Okay? So we're going to add 6 pi over 12 to get our first victim, our first real solution. All right. So if you add 6 pi over 12, negative 1 pi over 12 plus 6 pi over 12 is 5 pi over 12. Keep adding. 11 pi over 12. Keep adding. 17 pi over 12. Keep adding. 23 pi over 12. We're knocking on the door of 2 pi, and then we can't go any further. All right. Anyway, that's how you get the 8 solutions. I'll circle them in black. You should technically put them in solution set form. Although in the stress of an exam, I might let people just box these in. but these 4 from group 1, and these 4, not that guy, these 4 from group 2. Now, again, it's not a coincidence that we had 4x here and we had 4 in each group here, but it's not an ironclad rule because sometimes you have symmetries you're using. Maybe you're dealing with tangent or cotangent. Maybe you're dealing with quadrantal angles. So I'm not going to say it's an ironclad rule, but the fact there's a 4 there, it's not a coincidence. The fact that we have 4 from group 1, 4 from group 2. And again, you don't have to order these. Just make sure that all 8 are accounted for. And that's right? What a mess. Here we go. Pi over 12. Up there. 5 pi over 12. 7 pi over 12. 11 pi over 12. 13 pi over 12. 17 pi over 12. 19 pi over 12. 23 pi over 12. In fact, I sorted them in my list. You don't have to in yours. Sets are unordered.
Yeah, thank you. I understand that now. And well, no one else is asking any questions, but I kind of want to try the next 2 on my own. Is it okay if I do that tomorrow and email you if I can't figure them out?
You're welcome. Yes, and you could, for example, send me scans or something, and I'll be checking email. That's correct. Oh yeah. Oh, you're talking about Friday. Okay, now Friday. Let's see. I have a meeting 10 to 12.
If not, I can probably just have someone in Discord help me if I can't figure them out.
You know what? Let me just make a note for myself to check my email around 12:30. Yeah, and I should be able to get back to you by evening, I would think. So I'll just make a note to myself.
Okay, thank you. Unless if you want to do them right now.
It's up to you.
Or I can let you go because I feel bad keeping you too late.
Oh, no, don't feel it. So it's up to you. I mean, if a student would like to, take a crack at it, then I'd like to encourage the student to try it out.
Yeah. I want to try it out first because I just was just totally doing the wrong thing on that problem, and now I feel like I can get the other ones right easily.
Sure. So I think my meeting ends at noon, and then I'll remind myself to check my email around 12:30. But I should be able to get back to you by evening.
Okay.
Let me just write a note something. All right, so around 12:30 or so, I'll check my meeting schedule, but I'm sure sometime in the afternoon I can address it. Yeah. Okay, good. All right. Let's see here. Okay, so anything else? Anything else? Okay, I did the 6-4-10A earlier, right? I did 6-4-12-13, and then you'd like to try out the PQ. I think I've done the ones in chat. Yeah, we've done a lot of math. All right. I'll stick around. Any questions right now? Otherwise, I might take a 3-minute pause and ask you again. But any questions right now? Any questions?
I'm good, Professor. Thank you. Have a good night.
You're very welcome. Good night. Yes. Okay, so I'm going to do a 3-minute pause. Okay, so I'll be back at 10:07 and see if anyone needs anything. So back at 10:07. Let's see how things go. All right. So I'm recording, but if anyone wants me to stop or pause recording, let me know. All right, so 639. Okay, let me check that one. Okay, lots of stuff here. Save these. Okay, let's see, 639. 639. Okay, a rock is thrown. Yeah, this is resolving a vector. A rock is thrown with an initial velocity of Oh, okay. So all right, so let's take a look at 9. All right. Initial velocity of 27.3 miles per hour. Okay, may as well do a new page for this. Okay, we're at 152. Right. Lots of whiteboards. Okay, initial velocity of... All right, so here's the picture I'm looking at then. All right, so from the horizontal, 42 degrees, kind of like that, right? Okay, so this is 42 degrees. Whoops, 42 degrees. Okay, and we're just doing the initial velocity. We don't have the patience to follow the rock. It's just what's going on exactly at the moment the rock is thrown out. Okay, so initial velocity of... So 27.3 miles per hour is technically the speed. It's the length of this vector. 27.3 miles per hour. Okay. What is the rock's horizontal component? What's the rock's vertical component? Yeah. Okay. Resolving the vector. So the horizontal component is this. That's the horizontal component. The vertical component is this. Right angle. Okay. Now, the way the formula goes is, well, for the horizontal component for part A, oh, let me indicate that this is number 9, 6-3, number 9. All right. All right. Yes, good night. All right. Okay, so on part A, the horizontal component is given by basically, the idea is it's like an X. You're thinking kind of R cosine of theta, or instead of R, most books, when talking about vectors, would say it's the length of V times cosine of theta. But when you do polar coordinates in Calc 2, you're going to often think of X as like R cosine of theta, X being the horizontal component. All right, so what's that going to be? Well, 27.3 miles per hour, that's the speed, that's the length of the velocity vector, times cosine of 42 degrees. All right, so we work that out. Make sure you're in degree mode. And is it to the nearest 10th again, or 3 sig figs? 3 sig figs. All right, so what's that to 3 sig figs? Make sure you're in degree mode. Okay, I'm getting, what, 20.3 to 3 sig figs. Same measure of speed as before, miles per hour. All right. So that should be about 20.3 miles per hour. Yeah, 20.3 miles per hour, right. And then for the vertical component, I should have done this. You know what? I'll make this blue and make this, oh, jeez. All right, make this blue since I made A in blue. This is blue, and then this part in red, more consistent. Okay, yeah, because vertical component, that's B. Right, X is our cosine of theta. Y, guess what? Our sine of theta. Okay, although technically when dealing with vectors, R is the length of V. Yeah, okay, so then what's Y? Y, or the vertical component, the speed is still 27.3 miles per hour. And then sine of 42 degrees. And what is that to 3 sig figs? Make sure you're in degree mode. Y is about how many miles per hour? Okay. What are you getting? 3 sig figs? Well, I'm getting 18.3. Yeah, miles per hour. Technically, you should put the unit miles per hour. Yeah. Yes, I feel good. All right. Any questions? Horizontal component of velocity, vertical component of velocity. Basically, what's the initial speed of the shadow, right? The shadow against the floor and against the wall at the time the rock is thrown. Okay. Anything else? Anything else? See, any questions? Okay. Yes, you're welcome. Yes, thank you for your perseverance. Yes, lots of hard work. Oh no! It's my pleasure. No, I'm glad that you're putting in this effort. That's great. Oh sure. Let me know if you want me to move this thing. And remember, it's also in the video. So let me know when you want me to scroll up. Okay. Okay, good. Okay, you're welcome. Yes. Anything else? You can screenshot anything else. And again, this is all going to be in the video. Yeah. Unless you want me to trim it. Okay, good night. Yes. All right. All right, have a good weekend. All right. Okay. All right. Okay, very good.